Welcome. This is Calculus Fall 2020. My name is Scott Grizzard, University of South Florida. Just a reminder that there is a test this Saturday, and there is no class on Wednesday because it's Veterans Day. But I will be holding office hours. It is test week. I understand that, and I will be holding office hours. But there will be no scheduled class. There'll be no quiz for Wednesday. Okay, so let's go ahead and talk about the quiz. As usual, there are questions and polls in Blackboard Collaborate Ultra, and you may also chat and ask questions on Twitch, but just remember Twitch chat is public. Okay, let's go ahead and do this here. So, this quiz is an optimization problem, and it has a wrinkle. Okay? So what we want to do is we want to find, right, I've got the situation where I've got a farmer who wants to build a fence, right? And he wants to build it in the land adjacent to the north of his wall of his barn. So he gets to use the barn for part of the fence, right? That side's free. And on the west side of the plot, okay, he's sharing the fence with a neighbor who'll split the cost of the fence with him, right? They're good neighbors. The neighbor kind of wants a fence too, and they're going to share the cost, right? So, Canada's going to pay for half the wall. But the other two sides he's got to pay for himself. And fencing costs $20 a linear foot, and he's got $6,000. And then there's this wrinkle. So here's the situation, right? Here's the south side, north of the barn. So the south side is free. This is the side shared with the neighbor. This is the north side, and this is the east side. And those he's paying full freight for. And then there's this tree. This tree is 180 feet from the barn. So no matter what side he chooses, he's got to, right, if he wants 190 feet here, he can't do it. He wants to save this tree, so he's got 108, the maximum that's allowed is 180 feet. So the endpoints for L, so this is going to be some function of L, and the endpoints are going to be 0, less than or equal to L, less than or equal to 180. Okay, so 1 to 5, how do we feel about the drawing and kind of the interpretation of what's going on? Okay. All right. So the first thing we're going to do is we're going to find our equations here. Okay. So I've got my production function I'm producing area, and that is length times width. And this we want to optimize. So this is optimize production. So maximize production. So here's my production function. And here is my cost function. So in this chance, it actually is money, not building material or whatever else. It's money. So I've got 10L plus 20W plus 20L plus 0W, which is going to give me a nice combined equation of 30L plus 20W. Okay. So 1 to 5, how do we feel about our kind of setup there? Okay. Come on, vote, people, vote. There are 12 of you. We got 50% turnout. Okay, now we got a little bit more. Okay, are there any questions yet? All right, so now what I'm going to do is I'm going to combine this equation. So, I'm going to choose L to be the thing I solve for, just because that's the thing with my endpoints. I could choose W and then come back, but let's choose L. So I'm going to solve this for W. Sorry, the money we're going to spend is $6,000. So I'm going to solve this for W. And I wind up with 20W equals 6,000 minus 30L. And of course, I'm going to take out so that implies that W equals 6,000 minus 30L. And then I'm going to put 20 right here and 20 right here. Take a common denominator, split up the division. And then I'm going to do some canceling here, just to make my life a little bit more pleasant. So I'm going to wind up with a 300 here minus 3 halves L. All right, and now I'm going to sub this into that. And what I'm going to wind up with is A equals L times 300 minus 3 halves L, which equals, and then I'm going to set it up because I know I'm going to take the derivative and set it equal to 0, 300L minus 3 over 2L squared. Okay, so how do we feel 1 to 5 about getting those things all nice and happy? So one equation. Let's see, stop. One equation. Stop. Okay. So now what I'm going to do is I'm going to take the derivative and set it equal to 0. So I'm going to do dA over dL equals the derivative with respect to L of 300L minus 3 halves L squared. And that is going to equal 300 minus 3L to the first. And I'm going to set that equal to 0 because I'm optimizing. And I'm going to wind up with 0 equals 300 minus 3L, which implies that L equals 100. Okay. All right. And since 100 is between my endpoints, that's a critical value. So, values to check. 0, 180, and 100. Okay, so now I need to see if what I have is a max. Now, recall that there are 3 ways. So how do we feel about that? Taking the derivative, setting it equal to 0, and finding the critical values. So derivative equals 0 and finding critical numbers. All right, so now what I'm going to do is I'm going to check my critical numbers. Okay? Now, there are 3 things I could do here. I could check that this is a max, right? I need to kind of pick one. So I need to do one of these three things, okay? I need to either check the endpoints, do the first derivative test, or do the second derivative test, okay? So here's my thought, and it's just my thought. I know that a of 0 is going to equal 0, and my question requires me to compute the maximum area anyway. So I'm going to have to compute these two values, okay? Since I've got to compute the two values anyway, why not just compute them now? That's my thought. So A of the area, so I'm going to use this function right here, and I'm going to say A of 0 equals 0. So L equals 0, right? That's not going to be anything. A of 100 equals, with respect to L, so this is going to be 100 times 300 minus 3 halves times 100. And that's going to give me, this is going to be 50. This is going to be 150. So this whole thing is 150. So that's going to give me 100 times 150, which equals 1, 5, and 3 zeros at the back. And then A of, if L equals 180, which was the other endpoint, correct? Yes. Go away. So I'm going to take 180 times 300 minus 3 halves times 180. And that is going to be a calculator problem. This is going to be 90. 90 times 3 is 270. I can do math. So I'm going to wind up with 270. So I'm going to wind up with 180 times 270. Nope. 180 times 300 minus 270. Which equals, do a little math here, 180 times 30. Which equals, and somebody check my math here, because it is perfectly possible that I'm making a stupid mistake here. So that's going to be, what is that, 4? Yeah, that's going to be 4,400 if my math is correct. Nope, 5,400. Okay. Is that right? Somebody grab a calculator and confirm that for me to make sure I'm not messing it up. Okay. So how do we feel about this step here? Just kind of checking my stuff, 1 to 5. I got 3 values. Let me check them. Okay. And I'm going to write, okay, so 1,500 is the biggest, so the max is 1,500 square feet when L equals 100 feet. Okay. So now I'm going to solve for W because it asked me to do that. So let's see, where's my W here? So my W was 300 minus 3 halves L. So that's going to be 150 feet. And then A equals 150 times 100, which equals, put 2 more zeros on there, 1, 5, 1, 2, 3 zeros. Oh, I already did that earlier. Square feet. So the area is maximized when W equals 150 feet, L equals 100 feet for an area of 1,500 square feet. All right, so I've wrote down what I meant, and now I'm just going to check. Did I answer the question? Right? So, find the dimensions of the plot. I did. And state the area enclosed. I did. Okay. So 1 to 5, how do we feel about the kind of ending of that thing? And are there any questions? Okay. I could have done an option 3, right? I could have done this, but then I would have had to check my other endpoint anyway, right? I could have found that it was a max by doing this. And then I actually wouldn't have had to check that this point here. If I'd made the max element argument, I wouldn't have to check 180, and I wouldn't have to check 0. Okay? But I would have had to check this A anyway, so, you know. All right, so advice for doing these problems. These are really... Okay, first bit of advice. If you want some advice, here's the first bit. Draw. The second bit is don't label too early. And the third bit is, if you can't figure it out, impose an interpretation. Because that's how these kind of things tend to get graded, right? You've got this kind of area, correct cost, solving for the cost, substituting to find it, blah, blah, blah. And the other thing you have to do is practice. These are problems that the reasoning skill is the big deal, if that makes sense. Okay? So, you know, it's about that old joke. How do you get to Carnegie Hall? Well, practice, practice, practice. It's the same thing here. You really have to practice these problems. And I admit that some of the ones in the WebAssign kind of stink. But I was told I couldn't remove them. So I said, okay, yes, ma'am. Especially that cone one. I hate that cone one. But you have to play with it. That's basically what I can say. Does that answer your question? You have to play with these problems. Now, on the test, we tend to ask things that are kind of quick on the computation. At least we'd like to. Now, whether or not that's what happens this year is another question, because I'm not writing it. But we tend to ask things that you can do with some rapidity. It's hard to. It's easy to ask these kinds of area problems. It's easy to ask production function type problems. It's a bit harder to ask you to do the. It's really hard to ask you to do a cone problem. A cylinder problem is within the realm of possibility. Um, those box problems just take too long. But those cylinder problems are definitely within the realm of possibility because those are you can do the computation somewhat quickly. Um, Especially if you're willing to just sit down with a calculator and punch through them instead of figure out what their exact values are. Okay. All right. So let's see. Let's go on to the true false. If f prime of u equals 0, then f has a local minimum or a local max at u. Nope.
No. No.
Right?
No.
The opposite is true, right? If f has a local minimum or max, then f prime of u equals 0. But the converse there, the other argument, the converse is not true, right? Consider f prime of x at x equals 0, right? Here, I'm sorry, consider x cubed at x equals 0, right? Here, f prime of x, f prime of 0, f prime of x equals 3x squared, so f prime of 0 equals 0. But f has neither a min or a max. Okay. Should be a NOR. Okay, so 1 to 5, how do we feel about that? Okay. All right. On the other hand, so one direction is true, but the other is not. That's kind of the tough thing there. All right. If f prime of u equals 0 and f double prime of u is less than 0, then f has a local max at u. That's actually true, right? So I actually can determine this if my second derivative is moving. So if my function's concave down, and I have I have an f prime of x equaling 0 here, I actually do get the fact that that I have a local max. So that one's true. But I need more than just f prime of x equaling 0. One to 5, how do we feel about that one? Okay. If f prime is greater than 0 on an interval, then f is decreasing on that interval. Nope, f is increasing on that interval. That one's false. All right, so 1 to 5 on 2C. All right.
N-O.
All right. If f has a critical value at u, then f prime of u equals 0, or f prime of u does not exist. Yes, that's the definition of a critical value. All right, so 1 to 5. How do we feel about that one? Okay. And if f prime of x equals g prime of x for every x, then there exists a constant c, so that for every x, g of x equals f of x plus c. In other words, these two functions are vertical shifts of each other. And that one is true. That was one of the consequences of the mean value theorem. How do we feel about that one? Okay, are there any more questions? All right. So let me go ahead and end the stream here, and we'll talk about the problem set.